This is Dr. Hold. In this video I want to talk about how to find the moment of inertia about an assembly where I have three parts. This first one, I have one part. It's going to be a flat plate. It's going to have a mass of 2 kilograms. It's going to have the dimensions of 2 meters by 0.25 meters. I have another plate here. It has a mass of 1 kilogram. It has dimensions of 1 meter this way by a thickness of 0.5 this way. Third piece, the 1 kilogram, is going to have a length of 1 meter this way and a thickness of 0.5 this way. And I'll find the moment of inertia about this assembly as if it would rotate around this point here, as if a pin was coming straight out of the screen at you at this point. This assembly could rotate either clockwise or counterclockwise around this point here. To do this, I'll be using this moment inertia equation for the center of mass of each object as well as the parallel axis theorem. The moment inertia about a plate is going to be 1/12 the mass times a squared plus b squared, where a is going to be this distance here and b is going to be this distance here. I'm going to break these into three separate inertias and then add them together. When I'm done, I'll get the summation and the correct inertia for the overall assembly. I will start out by the moment inertia of number 1 about point A. Again, to do that, I will immediately go back to this equation here, because the first thing I want to do is find the moment inertia around its own center of mass. Now, its own center of mass of this object here is going to be right at this point here. So I go back and I do 1/12 times the mass, which is 2, times 0.25 squared plus its length squared. That right there is just the moment inertia about its own center mass. Now I do the parallel axis theorem plus the mass, which is going to be 2, times the distance from here, the center mass, to the rotational point. Since the object is too long, this distance will be 1. We will be squaring that. And when I run that number, I get 2.677 kilograms meters squared. Alright, so I'm done with that one. Now I go to number 2 to find the moment of inertia of number 2 as it rotates around A. Now, the thing you'll be careful in this one is you say, well, where is the center mass of this? Well, it's right there. What distance do I take when I do the mh squared when I use the parallel axis theorem? Well, I need to find out the distance from here. I want to use a vector. I want to find the distance from here to here. So first thing I do is I'm just going to find the moment inertia around its own center of mass. I use the same equation. I do I don't want to do it blue, I want to do it black. Hang on a second. Black equals to 1/12 times the mass, which will be 1 of number 2. That has a mass of 1, which I get labeled right here. Come down, I do, let's see what we want to do here. We want to do its height, which is going to be 1 plus its thickness. Again, this is not drawn to scale. So, alright, so now I'm going to come down and I'm going to put plus 1 times in parentheses. Now I'm going to take the square root of this. I'm going to do Pythagorean theorem here. I need to find out what this distance is. I know I'm going to come over, how far? I'm going to come over 2, but then I need to come back half that thickness, so that would be 1.75. Plus, how far am I going to go up from this center? Well, this is point, so I need to go 0.125 and then another 0.5 to get up there, or 0.625. Squared here. Alright, so again, this is the moment inertia around its own center mass, and this is using the parallel axis theorem, which is nothing more than mass times the distance from the point here to the rotational point, and we're just squaring that. Again, if you notice here, once you square, you're going to lose what's inside of the square root. So let me run that number. I have not run that particular one with a calculator. So 1 divided by 12 times 1 times in parentheses 1 plus 0.5 squared, okay, plus 0.75 squared, plus 0.625. That gives me a value of about 3.56. I'll do 3.557 kilograms meters squared. Okay, I come to part number 3. I3, rotating around A. Again, I will go back. I will do the 1/12. I will multiply it by its mass. It's sitting here, so I will do, again, it doesn't really matter whether you do B squared or A squared first, going to be adding them. So I know the dimensions are going to be a 1 by 0.5. Gives me 1 squared plus 0.50 squared. Okay, so again, that's the moment of inertia around its own center mass plus, and again, this time I need to find out what the distance is from here up here to the center of mass here. So if I do that, I will multiply again by its mass times in the square root of, and again, how far did I go? Well, I'm going to go exactly the same thing. I'm going to go horizontally 1.75. I will square that. Now, how far do I go up? Well, I got to go up 0.125 here. I'm going to go up another 1 and another 0.25 to get up there. That distance is going to be 1.375. So it's 1.375 going vertically up to the center mass here, and again, it's going to be 2 minus, or 1.75 from here over to here horizontally. So I'll put that in my equation, plus 1.375 squared here. Okay, ran that value here. Let's see what I got there. I believe, if I remember right, I got 5.0573 kilograms meters squared. Now the total moment of inertia is just going to be the summation of all that. So let's run those numbers real quickly. So I got 3 plus 5.0573. Let me move this out of the way. Plus 2.677. That gives me a total moment of inertia around A of 11.2916 kilograms times meter squared. And that is the parallel axis theorem. Again, and one thing you're going to note that I think is interesting on this part, if you go back to look in the original picture, even though I had more mass with this, these two objects had less mass, but they were further away from the rotational axes. As a result of them being further away, they created actually more inertia than they did with the part that had the more mass. The 2 kilogram mass only created 2.67 kilograms times meter squared of inertia, while the other two created greater inertia. So the summation, again, 11.2916. Hope this video was useful. Again, this is pretty much the technique you use for using the parallel axis theorem and finding the moment of inertia of an object rotating about a point.